Welcome all. In the last section, we discussed second law of thermodynamics. Today, we are going to discuss more properties of the thermodynamic function entropy. Here we discuss the relation between entropy and adiabatics. Let me draw a figure, a PV diagram. Here pressure is drawn along y axis and volume is drawn along x axis. It is an indicator diagram. Here I draw two adiabatics A1 and A2 very close to each other. Draw two isothermals AB, CD. AB is an isothermal at temperature T1, CD is the isothermal at temperature T2. Then draw another isothermals EF at temperature T3. Another isothermal at temperature T3. Here AB is the isothermal at temperature T1 and CD represent the isothermal at temperature T2, EF represent the isothermal at temperature T3. So, this form a four-sided figure AB, DC and this form a four-sided figure CD, FE. These four-sided figures represent a Carnot cycle. Consider the Carnot cycle A, B, D, C. Here temperature at temperature T1, Q1 be the quantity of heat absorbed and at temperature T2 it rejects a quantity of heat Q2 along the isothermal CD. So that in Carnot cycle we can write Q1 by T1. In Carnot cycle we can write Q1 by T1 is equal to Q2 by T2. Then considering another cycle CDPE, the quantity of heat absorbed at temperature T2 along the isothermal, let Q2 be the quantity of heat absorbed at isothermal CD at temperature T2. Then we can write the equation in Q2 by T2 is equal to Q3 by T3. And for another cycle the equation becomes Q3 by T3 is equal to Q4 by T4. These equations together connect an equation Q1 by T1 is equal to Q2 by T2 is equal to Q3 by T3 is equal to Q4 by T4 is equal to Q by T, a constant. This shows that the quantity Q by T remains constant during a transition between two adiabatics along any one of the isothermals chosen. Here Q by T represent, here the Q represent the quantity of heat absorbed or liberated at temperature T. Let A1 and A2 be the two adiabatics very close to each other. When these two adiabatics very close to each other, delta Q be the quantity of heat absorbed or liberated at temperature T, then the equation can be written as delta Q by T is equal to ds. Here ds represent the change in entropy and this in general this equation can be written as integral A to B delta Q by T is equal to integral S1 to S2 ds equal to S2 minus S1. Here S2 minus S1 represent the difference in function of the entropy from final state to initial state, and this function is called entropy. Let us see what are the properties of entropy. From the equation ds is equal to delta Q by T, it is clear that when the adiabatic process occurs, delta Q is equal to 0. Delta Q equal to 0 means during an adiabatic process, neither heat enter the system nor heat leave the system. Then this equation becomes ds is equal to 0. ds equal to 0 means change in entropy of the system 0. That means entropy remains constant during an adiabatic reversible process. So, an adiabatic reversible process is known as isentropic process. When heat is absorbed during a process, there is an increasing entropy, and when heat is rejected during a process, there is a decreasing entropy. Let us discuss change of entropy in a Carnot cycle. Let me draw a Carnot cycle. By drawing this, we again draw an indicator diagram PV. A Carnot cycle can be drawn by connecting, first we draw two adiabatics A1 and A2, and these two adiabatics are connected by drawing two isothermals at temperature T1 and temperature T2. Here AB is one isothermal at temperature T1 and CD is another isothermal at temperature T2. And here Q1 be the quantity of heat absorbed during the isothermal expansion at temperature T1, and Q2 be the amount of heat liberated during an isothermal compression at temperature T2. So, in this equation, from this figure, it is clear that Q1 by T1 is equal to Q2 by T2. Here, during the isothermal expansion, there will be a gain in entropy during the isothermal expansion, because here heat is absorbed during the isothermal expansion, and here a loss in entropy occurs because here a heat is rejected during the isothermal compression. So, here the entropy is lost. So, a negative sign is there. So, the equations become Q1 by T1 plus Q2 by T2 is equal to 0. Q1 by T1 plus Q2 by T2 equal to 0. That means this can be written as, in a Carnot cycle, delta Q by T is equal to 0. Delta Q by T, ds is equal to delta Q by T. ds is equal to 0. When ds equal to 0 means entropy remains constant. Entropy remains constant. When a system undergoes a Carnot cycle, the entropy of the system remains constant. Change of entropy in a reversible cycle. Let me draw a figure. A reversible cycle is drawn in a indicator diagram. Here A, B, C, D represent a reversible cycle. In order to obtain the change in entropy in a reversible cycle, we have to draw adiabatics in this reversible cycle. So, I draw number of adiabatics very close to each other, A1, A2, A3, A4, etc. Let me draw isothermal connecting these adiabatics with A, small letter A, small letter B, A dash, B dash, here C, C dash, here D, D dash. So that this figure A, B, B dash, A dash form a Carnot cycle. As I already discussed, in a Carnot cycle, Q1 by T1 plus Q2 by T2 equal to 0. This is for one Carnot cycle. Here, so many Carnot cycles are there. So, we represent this as delta Q1i divided by T1i plus delta Q2i divided by T2i is equal to 0. Here, this I for 1. When we replace I is equal to 1, this is for one cycle. Delta Q1 1 by T1 1 plus delta Q2 1 by T2 1. Then 1 2. I can take values from 1 to up to n. Then summation of I delta Q1i divided by T1i plus delta Q2i divided by T2i is equal to 0. Here, this is sum in different Carnot cycles. Then this becomes 0. So that for any reversible cycle, it can be written as in a closed integral. This closed integral delta Q by T is equal to 0. This is known as Clausius theorem. It states that the change in entropy for a complete reversible thermodynamic cycle is 0. Next, we have to calculate the change of entropy in an irreversible cycle. In order to describe the change of entropy in an irreversible cycle, first we consider a reversible process. In reversible process, we found that integral delta Q by T equal to 0. But in nature, almost all processes are irreversible. In an irreversible process, it is found that integral delta Q by T less than 0. That is, the negative part of the integral delta Q by T increases. Negative part of the integral delta Q by T increases. The proof of this can be done by imagine a body to be taken from the state A to a state B by an irreversible process and then brought back from B to A by a reversible process. That is, imagine a body A is taken from A to B through a irreversible process, and this B is taken back to A through a reversible process. So that making the whole cycle irreversible. This whole cycle become irreversible. For an irreversible cycle, we write delta Q by T less than 0. So, consider these two parts, integral A to B delta Q by T. This is for irreversible and this is for reversible. The whole cycle is irreversible, so that this sum of these two terms will become less than 0. So that this equation integral B to A delta Q by T represent a reversible process. It's already we get the result, integral B to A delta Q by T is equal to SA minus SB. That is integral delta Q by T is equal to ds, change in entropy of the two states. From this it is clear that when we take two states B and A, here this equation becomes ds means SA minus SB, change in entropy. Substitute this in this, then we get integral A to B delta Q by T plus SA minus SB less than 0. That is SB minus SA greater than integral A to B delta Q by T. In an irreversible change from state A to B, the difference of the entropies in the initial and final states is greater than the integral A to B delta Q by T. Then we have to go principle of increase of entropy. Whenever an irreversible process occurs, the entropy of the universe increases. Clausius related the second law of thermodynamics as every process, whether physical or chemical, progresses in such a way that there is a net increasing entropy. Next, we have to go entropy and available energy. In order to discuss entropy and available energy, suppose we have Q units of heat available at a temperature T1 and that the coldest reservoir available has a temperature T0. That is, there is two temperature reservoirs, one is at temperature T1 and other is at temperature T0. In order to obtain the maximum work or energy from these two, we have to operate a heat engine in between them. Then the maximum work or energy obtained will be, this heat engine should be Carnot engine. So, we get maximum efficiency. Then the maximum work is given as work related with efficiency of the engine by the equation W by Q is equal to eta, where eta represent efficiency of the Carnot engine. Then maximum work is given as eta by Q, eta into Q. Eta into Q. Here eta is the efficiency of the Carnot engine given as T1 minus T0 divided by T1 into Q, 1 minus T0 by T1 into Q. For the engine to operate, this heat must be transferred to the cylinder of the engine, and due to conduction, radiation, etc., this temperature will be fall to say T2. That means, when heat is transferred from the higher temperature reservoir to the engine through a cylinder, there will be loss in heat due to conduction, radiation, etc. So that the temperature will falls to T1 from T1 to T2. Then the actual work will be given as W dash is equal to T2 minus T0 divided by T2 into Q. Here the temperature is less than T1 temperature. So that the equation becomes 1 minus T0 by T2 into Q. W dash will be less than W. Here the W dash represent actual work, and here W represent the maximum work, and from this figure, from this expression, loss of available energy will be W minus W dash. W minus W dash, substitute in this equation 1 minus T0 by T1 into Q minus 1 minus T0 by T2 into Q. Then Q minus Q T0 by T1 minus Q plus Q T0 by T2. Here we cancel these two Q's, minus Q, Q, then minus Q T0 by T1 plus Q into T0 by T2 is equal to T0 kept outside, then we get the equation Q by T2 minus Q by T1 is equal to 0. Here this Q by T2 represent entropy of the system, then S2, Q by T1 represent S1. Thus, S2 minus S1 into T0 is equal to 0. Thus, loss of available energy is equal to gain in entropy into T0. In nature, however, almost all processes are irreversible, so that the entropy of the universe increases, making more and more energy unavailable. Available energy of the universe tend towards 0. This usually referred to as the principle of degradation of energy. The previous equation, from the previous equation we get loss of available energy is directly proportional to gain in entropy. Entropy of the universe tends towards 0, that is entropy increases in universe. As entropy increases, loss of available energy increases, that means available energy decreases, that is called the principle of degradation of energy. Next we go the expression connecting the two laws of thermodynamics. The two laws of thermodynamics are first law of thermodynamics and second law of thermodynamics. The expression is TdS is equal to du plus pdv. Then how this expression we get? From first law of thermodynamics, delta Q is equal to du plus p dv. Delta Q can be written as du plus p dv, that is when a quantity of heat delta Q is given to a system, it is utilized for increasing in the internal energy of the system and external work done. Here external work done is given as p dv. This is from first law. And hence from second law of thermodynamics, we get the entropy of a system is equal to delta Q by T. Delta Q by T is given as ds. Then delta Q is equal to T ds. Substitute this equation in the first equation, we get T ds is equal to du plus p dv. This equation connects the two laws of thermodynamics. Next we come third law of thermodynamics. Second law does not uniquely determine the reference state or even the difference in entropy. To remove this drawback about entropy, third law of thermodynamics was formulated. According to this law, the entropy of a system at absolute 0 is a universal constant which may be taken to be 0. Let me conclude the session. Today we discuss the properties of thermodynamic function entropy, the changes of entropy in Carnot cycle and in reversible process, irreversible process, then the connection between entropy and available energy. Then we last came the third law of thermodynamics. Hope the session was useful for you. See you next time. Until then, goodbye.